Hi, this is the MOSOMIC MEMS microphone guide. My name is Mikko Suvanto. In this episode, I talk about the electrical implementation of analog output MEMS microphones into devices. Stay tuned! This series is sponsored by Infineon Technologies. MEMS microphone interfaces can be divided into two groups, digital and analog. In this one I'll talk about analog microphones, and digital microphones will be handled in later episodes. A key difference between analog and digital interfaces in terms of system performance is their immunity to disturbances. Digital signals contain only two signal levels, one typically approximately 0 volts, corresponding to a digital 0, and the other one, for example, roughly 1.8 volts, corresponding to a digital 1. A disturbance in the signal line has to be relatively large, typically more than 0.5 volts, to cause a bit error, a shifting of the signal to a wrong value. Then again, analog signals are continuous signals that can contain all the voltage values between the minimum and maximum values. Therefore, even very small differences in the signal make a difference, enabling even small disturbances to deteriorate audio quality. That makes analog signals much more susceptible to disturbances than digital signals. There are cases and device types in which achieving a high signal quality with analog microphones is so challenging that designers and manufacturers have switched to using digital microphones almost exclusively. One such case is laptops, where the microphone output signal traces tend to be long, making them susceptible to disturbances, and they run in a challenging electromagnetic environment. Let's have a look at the goals for the electrical implementation of analog output MEMS microphones. Sound capturing performance is naturally high on the list of goals for a microphone implementation. The microphone system must maintain high fidelity between the incoming sound and the captured audio signal. In technical terms, this means having a low system noise level and a high signal-to-noise ratio, SNR, a flat frequency response, low signal distortion, in other words, high signal linearity, minimized disturbances such as RF interference, and minimized artifacts in the signal. Nowadays, a goal for many systems is high algorithm performance. A key method used to achieve a high signal quality or high system performance is using signal quality enhancing processing systems such as noise cancellation, echo cancellation, and directional systems. Also, speech recognition systems are popping up everywhere. The requirements set by algorithms may, in some cases, be slightly different from the requirements for good sound quality as perceived by human ears. For example, the requirements for frequency response and the width of frequency range may differ from each other. A key enabler for great sound capturing and algorithm performance is that the performance and functionality of the microphone system is stable and constant. In most cases, especially in the case of mass-manufactured devices, a system with mediocre performance and high operational reliability is likely to be preferred over a system with superior performance but questionable consistency and reliability. In the domain of electrical implementation of microphones, reliability can mean a few different things. Avoidance of malfunction, in other words, uninterrupted operation. Avoidance of reduced performance. A drop in the performance can mean, for example, a reduction in perceived sound quality or a deterioration of the performance and functionality of a signal processing system. Reliability and consistency require that microphones are able to operate as intended in normal electrical and electromagnetic environments that they face in devices. Achieving reliable and stable operation requires minimized variation from one device to another, from one microphone to another, of device and microphone performance and behavior over time, and minimized variation in the operating environment each microphone operates in. It can happen that, for example, one microphone may be sitting next to a hot component, such as an RF amplifier, and the other one is in a significantly cooler spot inside the device. There may also be differences in the electrical and electromagnetic operating environments, even within one device. Changes in the characteristics of microphones in relation to each other may reduce the performances and accuracies of functions such as ambient noise cancellation, echo cancellation, directional microphone systems like beamforming, beam steering, and source localization, and speech recognition and multi-channel recording systems. Key parameters to be matched in a multi-microphone system are, for example, sensitivity, frequency response, and phase characteristics. These parameters are affected by the properties of the microphone itself, but also the acoustical and electrical implementation of the microphone into the device. A key enabler for high and consistent sound quality is high electrical robustness of the microphone system. In many devices, microphones have to operate in a challenging electromagnetic environment that can put the RF immunity, power supply disturbance rejection capabilities, as well as ESD immunity of the microphone system to test. The choice of interface, digital or analog, can affect the results significantly. In general, digital is better than analog, and analog differential is better than analog single-ended. I'll go into more detail about the interfaces in this and the next episode. For a device designer and manufacturer, the easier a microphone or microphone system is to implement into the device, the better. A microphone should be easy to be designed to be a part of a system electrically, acoustically, and mechanically. This helps save resources, time, money, and nerves. Any challenges in the implementation are multiplied in devices with multi-microphone arrays. Ease of electrical implementation means immunity against reasonable changes in the electrical and electromagnetic operating environment of the microphone. Okay, now that we know the goals for the electrical implementation, let's see how we can reach those goals. Analog signals are more susceptible to disturbances than digital signals. Therefore, achieving a high-quality, disturbance-free analog microphone electrical implementation typically takes more effort than designing in a digital microphone. Due to the relatively unpredictable nature of some noise sources, such as RF interference, reaching a good design may require several design iterations and prototyping rounds. Designing the microphone implementation together with the rest of the device system improves the chances that the whole system works well together. It's also important to make sure that the microphone components are electrically compatible with the way they are implemented into the device. Parameters that could affect this are, for example, interface type, signal levels, frequency range, disturbance immunity, filtering, and grounding. Every aspect of the implementation has to be carefully designed. The components, such as capacitors, inductors, and resistors, the circuit design, the schematic, the layout of the circuitry and the components on the circuit board, the placement of the microphones in the three-dimensional space inside the device in relation to noise sources, the parts of the system that provide the right operating conditions, such as power supply and ground, and the parts of the system that receive the microphone output signal. The basis for a good microphone implementation is a good microphone component. It should have a low self-noise, high SNR, flat frequency response at the used sound frequency range, low distortion at the sound pressure level range the microphone will be used for, and good phase behavior. The microphone should also have high electrical robustness, immunity to radio frequency disturbances, to disturbances in the power supply, and to disturbances in the electrical ground. Even with a microphone that has very high electrical robustness, it's still important to make sure that the electrical implementation of the microphone does its job to also minimize the risk of problems. The implementation should provide the microphone a good operating environment and circuitry that enables getting the best possible performance out of the microphone. The environment should be reasonable when it comes to electromagnetic radiation. This is related to, for example, the proximity and strength of electromagnetic interference sources, such as antennas, switching amplifiers, and so on. The supply voltage and ground for the microphone should be as disturbance-free as possible and feasible. Clean supply voltage and ground can be achieved with, for example, physical separation from disturbance sources and with disturbance filtering. Separate microphone supply voltage from the supply voltages of noisier systems, such as the supply voltages of digital systems. Also, device charging systems and accessories, such as headsets, should be separated from the microphones to prevent disturbance coupling from them. The signal path for the output of the microphone must be designed to preserve the quality of the signal. Low noise, low distortion, and high dynamic range are key parameters to preserve. The dynamic range of the signal path should be so high that it doesn't limit the dynamic range of the microphone system. In practice, dynamic range is limited by the saturation point and thereby distortion of the signal path at high signal levels, and the self-noise of the path at low signal levels. The output signal level of the microphone must be correct in relation to the dynamic range of the signal path. The capabilities of the components or systems, such as amplifiers, that receive the microphone output signal must match the signal levels that the microphone outputs. To prevent addition of noise, the self-noise level of the signal path must be significantly below the noise level of the microphone output signal. The maximum signal level that the interface can handle must be so high that it can handle the maximum signal level that the microphone may output. The dynamic ranges of digital audio components in the signal path must be high enough to support the signal. I'll talk more about this in episode 19. If the signal is too weak, then the distance from the signal to the noise floor of the path may be too small, and this may degrade the sound quality in that path. There are a few things that can be done to avoid this. If needed, the signal should be amplified to bring it to the correct level. However, it should be noted that amplification may add noise to the signal, or it may amplify the noise that is already in the signal to a level at which it becomes a problem. Therefore, the amplification should be done before the noisy parts of the signal chain. The next thing you can do is to optimize the signal path in terms of noise. Low noise components should be used and appropriate measures taken to prevent noise and disturbance coupling to the signal path. In some cases, it may help to filter the signal to reduce the noise level. Also, a microphone with a higher sensitivity could be used. With a higher sensitivity microphone, the output signal level for a given sound input level is higher. However, this could cause problems at the higher end of the dynamic range. If the signal level is too strong as compared to the capabilities of the signal path, then the signal may approach or exceed the maximum level the signal path can handle. This will lead to distortion or clipping of the signal. There are ways to mitigate problems with too strong signals. You can increase the rail voltage of the signal path. You can also switch from a single-ended interface to a differential one. I'll talk more about this in a minute. One more cure could be to use a lower sensitivity microphone. However, this is likely to affect also the signal-to-noise ratio of the microphone system. In other words, the sensitivity of the microphone is a compromise between optimized noise level and headroom of the signal path. It's also important to make sure that the maximum signal frequency that the signal path can handle is high enough so that it doesn't limit the capabilities of the microphone system. There are typically direct current DC filtering capacitors in the output lines of analog microphones to remove the DC component from the signal. These capacitor values must be chosen so that they don't limit the bandwidth the signal line can transmit. 1 microfarad or higher capacitor values are commonly used. There may also be other filters or components in the signal path that may affect signal bandwidth. In ultrasonic systems, it should be noted that the bandwidth requirement may be tens of kilohertz. Another thing that the signal path must not compromise is phase. For example, filters can affect the phase behavior of the system. One important thing to note is the variation in microphones and in electrical components, as well as the variation possibly caused by device production. the implementation must take into account these component and manufacturing tolerances and the variations they may cause in the system. Optimizing a signal path in terms of disturbances is mostly about layout, shielding, and disturbance filtering. So, how does one avoid disturbances with analog output microphones? Choose an interface that is as immune to disturbances as possible. When using an analog microphone, a differential interface is a better option than a single-ended one. Whichever is used, the design of the implementation circuitry is still critical. In the device, separate audio systems from other noisy systems by placing them in separate sections on the circuit board. It is good practice to separate digital and analog circuitry to prevent noise coupling to the analog signals. Also, RF systems should be separated to their own section away from the microphone signals. High power signals are also potential noise sources. There should be no potentially disturbing signals near the microphone on any layer of the device circuit board. Grounding is one of the most important things to get right in the electrical implementation of a MEMS microphone into a device. Problems with grounding are likely to cause microphone signal quality problems, such as RF disturbances, signal crosstalk from other traces, and increased noise. The ground has several purposes. First of all, it provides a return path for the currents flowing in the device. The return currents coming from digital systems can couple to the analog systems, causing noise and interference. Preventing this from happening is one of the reasons why the microphone systems should be separated from digital systems. Second, ground is the reference voltage for the signal both at the microphone as well as at the system that receives the microphone output signal. Ideally, the ground voltage should be the same at both the microphone and the receiving end, but in practice the ground has some resistance, so the currents flowing in it cause voltage differences between different points in the ground. These voltage differences can deteriorate the quality of the microphone signal. The third purpose of the ground is to provide a place to dump unwanted high-frequency disturbances from the microphone-related signals. Directing the disturbances to the ground is typically done with filtering capacitors connected in parallel with the filtered signal lines. The star grounding system should be used in the device to help separate microphone return currents from other currents. This means providing dedicated return current paths for different components and systems. This will help minimize voltage differences in the ground at the microphone and the receiving end, thereby reducing the risk of signal quality degradation. All free circuit board area should be filled with ground. Ground near the microphone signal traces reduces capacitive coupling of high-frequency disturbances from other signals to the microphone lines. Another way to avoid disturbances is to keep signal traces short by placing microphones and other components close to each other. The longer the trace, the more efficient it is as an antenna that picks up disturbances. To prevent signal coupling, don't put sensitive microphone traces close to or parallel to noisy traces. Microphone traces should be crossed with noisy signal lines perpendicularly to minimize coupling. Also, the outputs of two microphones should be separated from each other to prevent crosstalk. Another way to protect microphone signals is to shield sensitive traces from electromagnetic radiation and from capacitive conduction from other signal lines. First of all, the microphone package should be a Faraday cage to shield the sound sensor and the microphone signals from electromagnetic disturbances. The protective Faraday cage can be extended to the device circuit board. I'll talk about this in more detail in episode 20. Since it's practically impossible to prevent all disturbance coupling to the microphone signals, there should be disturbance filtering on the signal lines. Many of the disturbances that threaten microphone signals in wirelessly connected devices are high-frequency signals that can be filtered out of the signal lines without affecting audio signals. Okay, let's talk about analog interfaces in MEMS microphones. They can be divided into two main types, single-ended and differential. The choice between the two interface types affects the implementation of an analog microphone significantly. The single-ended interface can be simple and cheap as long as signal quality requirements are not very high, or if the environment is not difficult. However, in recent years, the differential interface has become popular in high-performance microphone systems because it has some significant benefits versus the single-ended one. Differential interfaces are more robust against disturbances, such as RF interference and crosstalk from other signals. They transmit the microphone output signal in two complementary signal lines. The signals on those lines are opposite in polarity, and the effective microphone output signal is the difference between the two complementary signals. The illustration here shows a typical differential interface circuitry. The most prominent thing is that there are two output lines coming out of the microphone, out plus and out minus. There are capacitors in both output lines to get rid of DC components in the signals. The gain of the differential amplifier is set by choosing appropriate values for the resistors. The schematic also shows a capacitor, CF, physically placed close to the microphone to filter disturbances out of the supply voltage. As we can see, a differential interface requires two signal lines for each microphone, plus of course grounding and supply voltage that can be shared by multiple microphones if needed. If the circuitry and layout have been properly designed, the disturbances picked up by the two traces are approximately identical. When the signal is received with a differential amplifier, the interferences picked up by the two signal lines cancel each other, resulting in a clean signal. Another benefit of a differential pair is that it disturbs adjacent signal lines less than a single-ended signal. This is due to the fact that the electromagnetic field around a well-laid-out differential line is ideally zero. In other words, a differential pair improves the immunity to both crosstalk between two signal lines as well as the immunity of one signal line to the radiated disturbances that, for example, the device antennas transmit. The differential interface configuration also reduces the signal quality degradation caused by ground voltage fluctuations between the microphone and the system that receives the output signal. One more benefit is that disturbance coupling caused by coexisting return currents in the ground is suppressed. Thanks to its configuration, a differential interface also offers 6 dB more dynamic range than a single-ended interface when the rail voltages and MEMS sensor sensitivities are the same. This means that the maximum voltage amplitude is twice the amplitude of a single-ended interface. This enables increasing the maximum signal level of a microphone system without the need to increase the rail voltage of the signal line, enabling the capturing and transmission of higher sound pressure levels. It's important to note that all the potential benefits of a differential interface depend on the design and execution of the interface, the layout of the circuit playing a big role. The two signal traces in a differential interface must have matched impedances and lengths, and their layouts should be as identical as possible so that they pick up the same disturbances. This enables the cancellation of the disturbances when the signals are subtracted from each other in the receiving system. Single-ended interfaces are still popular because of their simple design and low cost. In a single-ended interface, the effective signal is the difference between a single output signal and ground. The downside to single-ended interfaces is that they don't offer significant protection against disturbances, such as radiated electromagnetic signals, crosstalk between signals, or ground voltage fluctuations. This makes designing the electrical implementation less predictable and increases the risk of schedule delays due to design revisions. The risk is especially high when implementing single-ended microphones into devices within which the electrical and electromagnetic conditions are challenging, like in most wirelessly connected devices. An advantage of a single-ended interface is that there is no pair of traces whose layouts and properties must be matched. There's also only one trace to protect and shield from disturbances. A single-ended interface requires 2 wires for each microphone, one for the signal and one for the ground or other reference voltage. The ground can naturally be shared by multiple microphones. The supply voltage can also be shared by a group of microphones. As you can see in the illustration here, a single-ended interface is simpler than a differential one. Okay, that's it for this episode. In episode 18, I'll talk about the electrical implementation of digital output microphones. I hope I'll see you around. Cheers! If you have any questions or comments, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation,